Hi there, my name's Roberto, and I'm with Project Neptune for the 2025 IEEE APS Symposium Student Design Contest. There's an emerging demand for real-time tracking of wireless sources, especially as our world becomes more wireless. We traditionally have done this through multi-channeled phased arrays. Only downside with those is that they're very complex. You need phase shifters, you need multiple input and output channels for each antenna on the array, and just the raw cost makes it not practical in a learning environment. So we're doing a switched antenna array in our scenario. It significantly makes design more affordable because we don't need phase shifters. Um, and it's readily available to be implemented. Our transmitter design is simple. We use some linear dropout regulators that don't give us switching noise and power VCO with it. Filter out the harmonics and then output it out of a monopole antenna. The main goal of the transmitter is to provide omnidirectional radiation for us to easily be able to find. Now, animated here is a plot of the radiated electric field magnitude. But these are the waves that we're looking for specifically. We can have our two antennas placed. And by knowing their spacing and the frequency of our signal, when we find our phase difference, this is coupled to the wavefront, and that is exactly how we get our angle. This is a triangular approximation, and it's the exact same if we reference the other antenna. The polarity or our phase difference will be different, but we just have a different reference point of view. So now a key difference that we used is that we had a spherical steering vector. This steering vector is made by finding the distance between our antenna and our transmitter. And we use that using the handy dandy Pythagorean theorem. And by using that distance relative to our wavelength, we can find the expected phase that we're going to see at our antenna. So this is a picture of the receive array. We have our 14 antennas and our 3D printed structure that holds it all together. So our antennas are modified Yagi-Uda antennas. They basically consist of a dipole and 5 directors along with a reflector back with the reflector backend. For our switching subsystem, we have two HMC 253 8-to-1R switches connected to each of our SDR's input channels. We then have our SDR outputting into a phase matched power splitter and connecting these both to channel 1 on each switch. This ensures that um, the path that these signals are taking is identical. And then we connect all of the odd antennas to the first switch and all of the even antennas to the second switch. All of these components are then controlled with an FPGA. And this gives us 13 phase differences to work with. The FPGA sets the TDMA schedule. When we look at the magnitude, we see that we have our window in about 1500 microseconds. And because of the accuracy of the FPGA, then we look at this on the SDR's point of view, we have this in samples. This first section is for finding this increased magnitude. And this second section is to actually save our phase differences that we're using. So the math simplified can be seen as, well, we have a list of normalized phase differences. If we take their pairwise differential, we end up with another list of numbers. So this second order differential is directly from the phase differences. And because our neural network needs values between 0 and 1, we can take the real and imaginary components. Now, because we have a ReLU activation function, any value from 0 to -1 will kind of be ignored. So we also include the negatives of these real and imaginary separations. So the visual example of the math is we have 13 phase differences that we've calculated using our steering vector. We take their pairwise differential and we split them into real and imaginary components. Now, seeing these real and imaginary components in terms of what our neural network will see is a little difficult, so let's add some color. You can see any value that is negative automatically turns black because our ReLU function won't see that. So this is kind of what our network is seeing in terms of a picture. In order for us not to lose data, we also include the negative components. Training itself is more of recording actual data points. So it's a little hard to see in this video, but we have a laser tape measure, and we shine the laser down our field of view, and with our digital protractor, we keep track of what angle that laser is pointed at relative to our array. So here's myself and Shivani. We're just training the array on a variety of points. And this training data is what we use to train the model itself. So in our GUI, we do have a button where it'll use the training data that we have and it'll begin to train the model. We use 32 batch processing with 10 epochs, and we use atom optimization to ensure convergence. And finally, we have just a good proof of concept showing that our receiver is tracking the transmitter in real time. These are our references, and thank you for watching.